Hey, so now we're going to talk about the positional encoding. So we know that the outputs of one layer are sent as the input to the next layer, but positional encoding lies at the input to the first layer. Now, if you've worked with NLP before, you know that typically before we used to feed things to RNNs, we had to embed our words. So we would have a vocabulary, and then we would have an embedding for each word in our vocabulary. Sometimes we would, depending on the problem, I guess, we would initialize our word embeddings with pre-trained word embeddings, such as with word2vec or glove or fast text or something, and then we would train additional words with nn.embedding. Now, RNNs have an inductive bias that their inputs, or the way that their models actually work, is inherently sequential. You have this notion of things going across time. However, transformers actually aren't. So in a transformer, when we have some input, so if we just say W1, W2, and W3, by default, when we build our attention matrix, there's no notion of which word should be first in the sequence, right? We have the attention weights of W2 with respect to W1, and W1 with respect to W3, and W3 with respect to W1, and so forth. But the fact that this is W1, for example, right here, doesn't actually make a sequential difference inside of this self-attention matrix. So what we need to do is we need to find a way to actually tell the transformer, hey, look, word 1 is first, word 2 is second, word 3 is third, and this is important. Having this order of words is important when you calculate your attention. And positional encodings are one way that we can inject positional information into the embeddings. So what we're going to do is we will have the embeddings for the words. So we're going to have embed some arbitrary word, and then we're going to have a positional encoding for the arbitrary location, and then we're going to add the two together, and this is going to give us our encoding that we're going to send to the first layer of our encoder. Okay, so how do we do this? Well, there have been a couple of methods proposed since the original transformer paper. The authors of the transformer paper, and this is what we'll be working with in this tutorial, propose using sinusoids to inject information directly into the word embedding. So they have two formulas which allow you to, and we'll look at this more, we'll look at the effect of this more in the next slide, but here I'll just break down the maths for you. So there are two formulas that we need to know. Let me just turn the pointer on again. Now, importantly, positional encoding does not depend on the feature of any word. We're not looking at the word itself. We're only looking at the position of the word, okay? So it doesn't matter whether the first word is a, or the, or position, or in, or max, or authors. All that matters is what position is the word in. The actual word itself doesn't matter. So our positional encoding formula uses sines and cosines, okay? And here, pos refers to the position of the word. So authors is position 1, propose is position 2, using is position 3. And I refers to the index inside of a hidden vector. Okay, so if I had if I had some vector here, and let's say this is 4 dimensions, 1, 2, 3, 4. I refers to one of these dimensions. So 2i is basically saying all the even dimensions, and 2i plus 1 refers to all the odd dimensions. Okay? So, I mean, we zero index things, so this is, you know, index 0. Let me just because we'll be looking at this in code in a second. So we'll just change this to a 0 index. So this is 0, 1, 2, 3, and we'll have values here, so whatever these values are, doesn't really matter. So what we're saying is for all of the even indexes, so we'll have word 1, and then we'll have word 2. So let's just call this y. Again, it doesn't, or x, yeah, just x. It doesn't matter what these actually are. What matters is the index. So here we have one argument to the positional encoding, which is the word. So either it's word 1 or word 2. And then we have the index inside of the vector. Okay, so 2i will refer to 0 and 2, and 2i plus 1 will refer to 1 and 3. Okay, so for the even indices, so we'll have word 1, and for the even indices inside of this vector, we will apply this formula. We will say sine of pos, so 1, or I guess 0 in some cases, divided by 10,000 to the power of 2i over d, and then we will have the odd case here, or not the odd case, the odd indices of the d-dimensional vector. Okay, so we would still apply both the sine and cosine to one word. So for word 1, for example, we'd be applying both these positional encoding formulas, and depending on the index inside of the vector, we will apply the sine or the cosine variant. Okay, let's take a look at a pseudocode implementation here. So this isn't actually how we're going to implement it in our code. This really just gives you a conceptual understanding of how you would implement it in its bare bones. We have a slightly more efficient implementation, and I'll run you through, I'll do a breakdown and a little live code demo of that when we reach the code. Okay, so what we're going to do is we're going to initialize a positional encoding matrix, which is max t by d. Okay. Now, max t is kind of just the maximum sequence length we ever want to support in our model. For example, 5,000, that's longer than any sequence length that we'll feed in. We'll probably be feeding in, I don't know, sequence lengths of 40 or 50 or something like that. The reason that I made this distinction is because the positional encodings are fixed. As I said, it doesn't matter on what the word actually is. It just matters on the position of the current word. We just want to say word 1 is word 1, word 2 is word 2, word 3 is word 3, and inject that position encoding into the transformer. So once again, the word itself doesn't, or the feature of the word doesn't actually matter. Okay, so we're going to initialize our positional encoding matrix. So this is just going to be, we'll just start it as zeros, and then we'll say, hey, look, we're going to have something which is max t by model dimensionality. So for every position in our max t, so for every word, hypothetically, right? So for word 1 of 5,000, for word 2 of 5,000, for word 3 of 5,000, for I in range d, so let's say our d is just hypothetically 100. So we're going to say, hey, so the first I is going to be 0, then it's going to be 1, then it's going to be 2, and so forth. If I is even, so if I modulo 2 equals 0, then the matrix, this zeros matrix at word 1, so or word 0, right? This should be word 0, and this should be word 1. So the first row at index 0, so this will be the very first iteration at word 0, so the first row and the first index of this row, we're going to apply this this formula. Okay, and if it's odd, so here we'll still be in the same pos loop. We'll be doing for if the index dimensionality is odd. So here with the first iteration where I is 0, we'll be applying this formula. Then I will be 1, so this second condition would be true. So we'd say, hey, pos is 0, I is 1, and then we'll apply this cosine formula. Then we'll loop over again. I will be 2, so this first criteria would hit, and then would say for word 0, for the third index in word 0, we'll apply this sine formula here. Okay, and then we'll do this d amount of times, and then we'll move on to the next pos. So the next pos would be word 1. So for word 1, we would be looking at the first row and would basically just perform that logic that we just ran through with this inner for loop, but over the first row instead of the 0th row. So okay, and then once we've constructed this PE matrix, what we do is we embed a word. Okay, so now let's say we have this positional encoding matrix. We'll then have our input sequence, right? And in our input sequence, we would embed each of the words. And then what we'll do is we'll say, hey, is this the first word? If it's the first word, then we'll take PE matrix 1 and then, or PE matrix 0, because 0 index, and then add it to the word embedding. If pos equals 2, and let's say we have some arbitrary embedding of 1.0, 1.1, 1.2, then what we're going to do is we're going to add PE matrix 2 to this embedding. So here D would be 3, okay? So how does this look? Well, this graph took me a little while to understand, but here across what we have at the bottom is the depth of our vector. So here, this is a 128 dimensional vector. So D is 128, okay? And this is the position of the word, okay? So this will be a word in position 0, and this will be a word in position 50. Okay, so we can see here kind of the magnitude of how the positional encoding affects what's actually going on inside of the, or if we were to visualize our positional encoding matrix, this is how it would look. At 64, everything is cut off and there's no information about the position. But until we hit 64 dimensions, we can see that based on the position of the word, the different indices in our vector would have different values. Okay, let's look at how to actually implement this in code. So first of all, I'll just get started with just the embedding layer first of all. We're not going to be using any pre-trained layers here. We'll just be learning the embeddings from scratch. Obviously, in a real system, yeah, definitely use some BERT embeddings, or if you're a bit more old school, some GLUB or Word2Vec embeddings or something like that. Here, we're just learning them from scratch. So our constructor takes in a vocab size, a padding index, and a model dimensionality. And in the real system, in our actual transformer system, we'll have a word embedding matrix for the source sentence and a word embedding matrix for the target sentence. The target language, sorry, the source and target languages. So we'll have two embedding matrices. Now, both of the embedding matrices will be of size D model, and we're just initializing a empty embedding layer of vocabulary size by D model. Okay. One thing I didn't mention in the theory is that in the original transformer paper, they multiply all the embeddings by the square root of D model. Okay, apart from that, it's pretty straightforward. We have our input, and our input length is, or our input shape is just going to be batch times sequence length. So this will just be, hey, we're, you know, this is word 17, this is word 343, this is word 2654, and so forth, okay, based on our vocabulary. We will then embed these to get our D-dimensional vectors. Okay, let's look at positional encoding now. So here I'm going to I'll run through this, and then we'll see what it's like in I should be able to do it here actually instead of a terminal. It might be a little bit nicer. Okay, so for our positional encoding class, we're going to take in D model and max sequence length. We're also going to take in a device, because basically we're initializing a matrix, a new matrix inside of the class. So we need to know what device to project that to. By default, it will initialize on CPU, but obviously we want to put it on GPU if we're training on GPU. So what we'll do is we'll construct our positional encoding matrix. And this is going to be our max sequence length. So this was max T in the theory, and our D model. Now, instead of using a for loop, we're going to use matrix maths to actually do this, because it's a bit more efficient than looping over every individual element in the positional encoding matrix. But we can see how this plays out to be exactly the same. Okay, so let's do it here, and we'll just use toy numbers so we can see what it's like. Okay, so torch.zeros, and let's say our max sequence length is 10 and our model dimensionality is 4. And if we just run this, we can see that we have 10 elements down and 4 across. So this is a 10 by 4 matrix. Okay, and now what we're going to do is we're going to create a list of, or we're just going to have a range of numbers, one for each of the indices. Okay, so this is pos, line 11 in the code. So a range will basically just create a list between two ranges. So here what we're going to do, we're going to say pos equals torch.arange 0 to 10. And we're going to unsqueeze that just for shape compatibility. You see this is a rank 2 tensor, so 1, 2. Here our A range would be 1, but just to have everything in like a rank 2 tensor, we're going to unsqueeze it. Unsqueeze 1. Okay, so here we have a list basically, well not a list, we have a range of numbers from 0 to 10, each in their own dimension. So the shape of this will be 10 times 1, or 10 by 1. If we do pos.shape, it's without this, 10 by 1. And one thing we're going to do is we're just going to convert this to float, because otherwise PyTorch will complain in our future operations when we try to use ints with or longs with floats. Okay, but this will be basically the same. If I just run this, we'll just see 0.0, 1.0, etc. Okay, cool. Now we're going to indicate whether something is an even indice or an odd indice. So this will be done along our rows. So here we're going to say this is this first one is even, this is odd, this is even, and this is odd. Okay, so we start with 0 indexing, which is why this is considered even. This will be the first index, hence it's odd. So this will be 2i equals torch.arange 0 to dmodel, which is 4, and step equals 2.float, and then let's print 2i. Okay, so because we only have 4 elements, what we're saying is like, hey, from 0 to dmodel, which is 4, in steps of 2, create me this list. Okay, so here we just have half of, because we're taking steps of 2, here we just have half of the elements that we would have had otherwise. So if this was 10 by 6, so if we had 6 dimensions across here instead of 4, then this would obviously be 0 to 4. Okay. Now what we're going to do is we're going to work out the divisor term. So this will be in the theory. This is basically this division symbol here, the denominator of each of the signs and the cosines. You can note that they're both 10,000 to the power of 2i over d. And note here, the reason we use I and not 2i in our actual code is because mathematically 2i is just being used to refer to the even indices, whereas 2i plus 1 is used to refer to the odd indices. Okay, so our div term equals torch.power. So we're just going to fix this constant, right? And we're going to say for every even indice that we have, so for all of the even indices in our list, we're going to run this division term by that. I'm missing a bracket somewhere. Yes, I am. Okay. So we're saying 10,000 to the power of this. Okay. And then what we're going to do is, sorry, I made a mistake. This isn't the even indices. This is just the two i's that we've obtained. Okay. Okay, where was I? Now we want to consider the even indices and the odd indices. So the even indices will be given by 0, and then from 0 we take steps of 2. And then the odd indices are from 1, we take steps of 2. Okay, so this will be 0, 2, 4, 6, 8, so forth. And this is 1, 3, 5, and so forth. Okay, and now we actually perform our pos. So this will be the position of the word. So here we've assigned this as this list. So each position of the word, what we're going to do is we're going to divide it by the divisor term that we've just created. And then we're going to perform a sign operation on top of it. Okay, so let's just look at pos by div term first of all. Okay, so we have a two-dimensional list, and we can see that for each of the indices we've had, the first has been divided by, or we'll take this pos list, and firstly we'll divide the number by 1. So 0 divided by 1 is 0, 1 divided by 1 is 1, 2 divided by 1 is 1, and so forth. And then we'll divide it by the second in this, the second thing in the div term, so 100. So 0 divided by 100 is 0, 1 divided by 100 is 0.01, 2 divided by 100 is 0.02, and so forth. And now what we'll do is we'll apply a sign operator on top of it. But what we're doing is for all the, but we only want to affect the even indices when we do this for our positional encoding matrix, right? So note that this is half the size, as in this is 10 by 2, right? And across the final dimension, that's half the size of what our positional encoding matrix is. So if I just do PE again, just so we can remind ourselves, we're going to be applying this to the even indices in our positional encoding tensor or matrix. Okay, so let's look at let's do this, and then we can visualize the outputs. So for all the even indices, we'll do a sign over the positional matrix divided by the div term. Okay, so we can see that for all of the even indices, so 0 and 2, we have numbers in them, and everywhere else we have 0. Okay, so in the odd indices, what we're going to be doing is we're going to be applying the cosine variant instead of the sine variant. Just to make this a bit clearer, let me just get rid of the sign up here, so we can see that these numbers are basically what we obtained up here, and then we've applied the sign operator on top of them. Okay, so we can see that what we got when we printed pos divided by div term was this tensor here, and we see that in the first column we have that 0 to 9, and in the third column, or the second index, we have the 0.0 to 0.09. Okay, so let's just go back to the sine term. And now we basically do the same, but for cosine. And the cosine affects the even indices, the odd indices, right? So we're going to start from column 1, and then for every second column after column 1, so we're going to skip 1. So here, this is just PE 0, 1, 1 equals torch.cos of pos div term. And we print PE. Oh, whoops, sorry, I typed that out wrong. Okay, so we can see that for all of our odd columns, so this column and this column, we've applied the pos divided by div term and then with a cosine operator on top of that. Now, the shape of this is 10 by 4, but we need to account for batch size. So what we're going to do is we're going to unsqueeze it, and then this will make it, this allows us to broadcast the same matrix over all of our batches. So that's what the unsqueeze does. And then we're going to register the buffer, and what this does is it does two things. First of all, it saves the argument as a class variable. So now we would refer to it in our forward method as self.pe. And secondly, what it does is is when we save the model, it will serialize this alongside the model as well. So think of it like a parameter which isn't learnable, okay? So the same way that in our linear layers, we have parameters which are learnable, this is a parameter which isn't learnable, it's fixed. Now in the forward method, what we're going to be doing is we're going to be receiving an input. So first, we'll send our tokens into the embedding layer. So this is batch times sequence length, and then we embed it, so we get batch times sequence length times model dimensionality. Now after embedding it, we're going to be sending it to the positional encoding layer. So this is batch times sequence length times model dimensionality, and what we want to do is we want to apply the positional information to it. So here we want to the sequence length, so this is index 0, this is index 1, and this is index 2 of the shape. We want to only apply however many whatever the sequence length actually is, right? So if our sequence length is, I don't know, 30, for example, we only want to take or with this use case, if our sequence length is only 4, for example, we only want to take the top 4 positional encoding information, and then we're going to add it to our input, okay? So here we're saying our truncated positional encodings are going to be everything up till, so we're going to take the whole batch, and then we're going to take everything up till whatever the sequence length of our input is. So again, if it's 6, then we're going to take only the first 6. And then we're going to add, so now positional encoding and X have the same shape. We're going to add the positional encodings to X, and then we're just going to run dropout and return it. The reason we have detach here is because we're not trying to actually learn the positional encodings. As I said, they're fixed, and all we're doing is we're trying to apply the positional encodings on top of the input tensor. Okay, let's take a look at this through running the example. So here we're going to have some toy inputs. So this will be 1, 2, 3, 4, and then we're going to have 2 padding indexes. So this will mean our sequence length is 6. The active elements in this particular input are going to be 4. Okay, so here we see 1 by 6 by 4. So we have a sequence length of 6, and we can see that after the embedding layer, so this will be here. After the embedding layer, the last 2 elements are zeroed out because we have a pad index of 0. And the first 4 elements actually have values in them because these are the first 4 elements which have values in them. Now we're going to apply our positional encodings. So we'll just create our positional encoding layer and specify what our model dimensionality actually is. To our positional encoding layer, we'll feed in the embeddings that we've just obtained. Okay? And this gives us our encoding for the first layer of the encoder. So what I mean by this is now this is what we'll feed in through our first encoder, and after the encoder runs and it gives an output, that output will be fed into the next layer of the encoder as we've just been talking about over the past couple of days. Note that here we see that despite in the embeddings, these last 2 rows were 0, and that makes sense because these were meant to be padding, that the addition of the positional encoding has changed what the values of these each of these words actually are. Now this is where the mask comes in that we ran through in the encoder layer. We'll talk about it a bit more when we get to masking itself, but just at a high level to provide some intuition, our mask would basically say, hey, look, where there was actually padding in the input, don't consider these tokens for when we run attention. So despite these actually having a value, we have some information somewhere else through the mask that these last two indices, or these last two words, were actually non-existent and they were just padding information. And we don't actually want to perform any calculations over the padding, we just want to perform calculations over where words actually existed. Anyway, that's it for positional encoding. This is probably one of the less intuitive aspects of the transformer, so if you manage to understand it, I'm absolutely glad with that. And I'll see you next time when we actually run through implementing the encoder in its entirety. Bye.